Hello everyone, this is Arije Docus, and let's dive into the core of our research by looking at the methodology where we were faced with a unique challenge. 26% of our dataset, over 8,500 genomic samples, were unlabeled. They had no clear resistance signal. So if we had used a traditional supervised learning approach, we would have had to discard all that potentially valuable information. So to solve this, we didn't just build one model, but two distinct supervised models. Think of them as two different strategies to leverage this unlabeled data. First is the the first model we had to deal with is the label propagation. This is a graph-based transductive model. Imagine creating a vast network or graph where each patient is a node connected to others based on how similar their genomic profiles are. Label propagation works by taking the confirmed resistance labels from the known patients and letting them flow through the graph to the unlabeled, but genomically similar neighbors. It is a very elegant mathematical way to infer the labels. The second model, we use the self-training XGBoost. This is a wrapper-based inductive model. It starts by training a standard XGBoost model on just the confirmed cases. Then it uses that model to predict labels for the unlabeled data. If the model is extremely confident in a prediction, we set a threshold of 90%. It pseudo-labels that data and adds it to the training set. The model then retrains on this enlarged data set, and the process repeats. This iterative loop allows the model to gradually learn from the unlabeled data. So the key difference is deployment. Label propagation is transductive, meaning it can only classify the unlabeled nodules already in its graph. It can't predict for a new patient walking into a clinic tomorrow. The self-training XGBoost model, however, it is inductive. It learns a generalizable function, so it can make predictions for entirely new patients based on their CD4 count and their genomic profile. So this makes it the more practical tool for the clinical decision support, which is why our selected model. So the label propagation architecture, let's unpack the label propagation architecture a bit more. So the workflow is straightforward but powerful. Step one, we have the data preparation. We start with our full data set, which is split into two groups, the confirmed patients with the known outcomes and the undetermined records that crucial 26% of the unlabeled data we want to classify. Then step two, we have the graph construction. This is the heart of the system. We build a weighted graph. Every single patient, both labeled and unlabeled, becomes a node. We then draw the edges between the nodes and assign them a weight based on how similar their feature profiles are. The similarity is calculated using the RBF canal, which is ideal because it creates a smooth, continuous gradient of similarity, perfectly reflecting the progressive nature of the immune decline in HIV. Then the third step, now the algorithm goes to work. It propagates the known labels, treatment success or failure from the confirmed nodes outward through the edges. The strength of the push is determined by the edge weight. Highly similar patients share more label information. This process runs iteratively until the labels across the graph stabilize. Then the next step, once the algorithm converges, Every unlabeled node now has a predicted probability of treatment failure. We then evaluate the model's accuracy on a held out test set of the confirmed patients on, and then the data it has, the data it has never seen during the propagation process. Then next we have the XGBoost system architecture. So this one, it is more dynamic, an iterative process. So the loop begins, we start with our initial supervised XGBoost model, trained only on the confirmed patient data. So the pseudo labeling step, this trained model is then used to predict outcomes for the entire pool of the unlabeled data. But we don't just accept all the predictions. We apply a strict confidence threshold of something 90%. Only the predictions where the model is at least 90% certain are promoted to become the pseudo labels. Then these high confidence pseudo labeled samples are then moved into the training set. The XGBoost model is retrained from scratch on this larger segmented data set. Then this cycle of the predicting threshold and training repeats with each round. The model's knowledge grows, and it can often confidently label more complex cases. The process typically converges in 3 to 7 rounds, and the final output is a robust inductive model ready for deployment. This architecture is powerful because it's conservative. The 90% threshold is deliberately high to minimize the risk of introducing noisy and incorrect labels that could degrade the model's performance, and a critical consideration when dealing with the clinical data. Then when you go to the label propagation, learning, and optimization, let's go a bit deeper into the brains of the label propagation model, mostly like how does it actually learn. So learning here is not like a neural network with gradient descent. Instead, it finds a unique stable solution to a system of equations. You can think of it as labels, uh, as labels flowing through the graph until they reach an equilibrium. And the final label for each enabled node is a weighted average of its neighbors' labels. So, and this process has a closed form mathematical solution that is guaranteed to be optimal and unique. On the optimized side, we had to tune the hyperparameters. The kernel, so as I mentioned, we chose the RBF kernel over the simpler k-nearest neighbors approach because it captures the continuous nature of the immune decline much better. Then we go to the max iterations. These are just safety stops. We set a maximum of 1,000 propagation rounds, but the algorithm is told to stop early if the label values stop changing significantly by more than 0.001. In practice, it converges much faster. And the most important hyperparameter we tuned was the gamma. Think of gamma as controlling the reach of a patient's influence. It defines the bandwidth of the RBF similarity canal. So if gamma is too small, the influence is very local. The graph becomes disconnected and the label can't propagate to distant but potentially related to enabled nodes. Then if the gamma is too large, everything looks similar, the influence reaches too far, and you get over smoothing where all the patients, regardless of their immune status, they end up with the same predicted risk. So we performed a grid search over the several gamma values, and we selected the one that gave the highest ROC AUC score on a validation set. For the self-train, next we go to the self-training XGBoost learning and optimization. So how the XGBoost learns? The XGBoost builds predictions incrementally, and it starts with a simple initial guess. And then in a boosting round, it can build a decision tree to predict the errors of the previous model. It ends this new tree to the sample slightly, improving the overall prediction. This process repeats for hundreds of rounds, and then each tree is built using a random subset of the data and a random subset of the feature. So this randomness is what prevents the model from overfitting to the noise in our clinical data set. Then how self-training expands learning. As we discussed, the self-training loop wraps around the XGBoost learner. It starts with the confirmed data and over several rounds intelligently incorporates with enabled data. The confidence threshold is 0.90. And this is the most crucial hyperparameter here. A lower threshold would bring in more pseudo labels faster, but with a much higher risk of introducing the clinical noise that could bias the entire model. In this domain, 90% confidence is the minimum we consider defensible. We also tuned the core XGBoost hyperparameters to find the right balance. The maximum depth was 4, so we keep our trees shallow. This prevents any single tree from memorizing very specific noisy patient details, and it forces the model to learn the broader or the more generalizable patterns. Then next we had the N estimators, and those ones were equating 200 boosting trees, and the learning rate is 0.05. This is a classic trade-off. We use 200 boosting rounds, but with a small learning rate. Each new tree makes a tiny adjustment to the prediction, leading to a much more stable and carefully optimized final model. Then we have the scale pose weight. We automatically handle the class imbalance where 55% of the cases are no failure by telling the model to give more weight to the minority failure class during the training. So it doesn't just learn to predict. There is no failure for everyone. Then when we go to the explainable AI model audit, having the accurate models is only half the battle. In a clinical data setting, a doctor needs to trust the model's recommendation. They need to know why it predicted a high risk for a specific patient. And this is where the explainable AI or XAI comes in. We performed an XAI audit on both models using the different techniques best suited to each one to verify that their predictions were based on the sensible clinical factors. So since the label propagation doesn't provide its own feature importance scores, it works on a distance matrix. We used a model agnostic feature called the permutation importance. So the logic is beautifully simple. We take our held out test and measure the model's performance. Let's say it is F1 score. Then we take one feature, for example, the CD4 count, tire, and randomly shuffle its values. This breaks any relationship between the feature and the true outcome. If the model's performance drops significantly after shuffling, it tells us that the model was relying heavily on that feature. If the performance stays the same, the feature wasn't important. So we repeated this for every feature, and the results confirmed our clinical hypothesis. CD4 count showed the highest importance. This is a major validation of our core premise. The model had learned that the patient's level of immune suppression is the single most critical factor in predicting the antimalarial treatment failure. So the genomic markers like the anti-resistant and CQ resistant also ranked very high, which is expected, and they are direct drivers of the parasite resistance. And the geographic region showed moderate importance, reflecting the regional overlap of HIV and drug resistance. We saw our exploratory data analysis. Interestingly, the year feature had lower importance, acting as a proxy for the data quality, confirming our finding that older data is less predictive. Then for our selected XGBoost model, we used the more sophisticated XAI method called the SHARP. So the SHARP is grounded in game theory and provides a beautiful, consistent way to see exactly how each feature contributes to prediction. We use the three key SHARP plots: the bar chart, the beesworm, and the waterfall plot. So the bar chart gives us a global ranking of the feature importance, similar to permutation importance. It shows the average impact of each feature on the model's output. We can immediately compare this to the label propagation results and see if the models agree on what's important. They do CD4 tire and the key resistance markers are at the top. Then the beesworm plot, that's at the bottom, it's incredibly informative. Each dot represents a single patient prediction. The position on the x-axis shows the sharp value, how much the feature pushed the prediction towards the failure. Then, yeah, those are the positive values, or away from it, those are the negative values. The color of the dot shows the actual feature value, red for high, then blue for low. Look at CD4 tire. We see a clear trend where the low CD4 counts the blue dots. They are clustered on the positive side, pushing the prediction towards the failure. While the high CD4 counts the red dots, they push towards success. This is exactly what we expect clinically. And for a resistance marker like CQ resistant, we see that the presence of resistance, the red dots, strongly pushes the prediction towards failure. Then the waterfall plot is for a single patient. It's just that the model's baseline prediction, the average risk for all patients, and then shows how each feature's value for this specific patient adds or subtracts from the baseline to arrive to the final prediction for a clinician. This would be an incredibly powerful tool. They could see, for instance, that patient X has a high predicted risk of failure, primarily because of their low CD4 count and the presence of a terminism resistance marker despite being on a generally effective drug. This level of detail provides and uh, a clear and a trustworthy explanation for the model's recommendation. So this is all helpful. Now, have a nice time.